coupled circuits, and there is also electrostatically coupled circuits. But in our syllabus, we have got only magnetically coupled circuits. So in that, we have discussed about the Faraday's first law and second law. So due to that, an EMF will be induced in a current carrying conductor. So that EMF can be classified as self-induced EMF and mutual induced EMF. So that is exhibited by self-inductance and mutual inductance respectively. So self-inductance is nothing but physically measurable. So the mutual inductance is not physically measurable. So it is an imaginary quantity. Okay. So whenever you hang a coil like this, L1, and which is carrying current I1, so it generates flux phi1 around it. So, and if it is linking a coil L2, so what it does, it also generates some flux inside it, and due to that, current will be generated, and due to that, EMF will be induced. Okay, so that is what we have discussed in the last class. And also, due to the current flowing in this coil, there will be some flux linking this first coil. So that also generates some EMF in the first coil. So altogether, the cause will be opposed by the effect always. The cause here is the current, and the effect is here is the induced EMF. So it affects the supply voltage. So it opposes the supply voltage always. Clear? So this is what we have discussed, and also we have discussed about the coupling, that is coefficient of coupling. So M. So M we can denote in terms of what rate of change of flux. Okay. So linking the coils. Based on that, you can denote it mutual inductance and coefficient of coupling. So when L1 and L2 are linked, we can denote coefficient of coupling K as M by square root of L1 L2. K, the maximum value of K is 1. So if K happens to be equal to 1, then all the flux coming out of the coil number 1 links the coil number 2. That means it is tightly coupled. That means it is tightly coupled. So if it is loosely coupled, what happens? The flux which is emanating from the first coil, the complete flux will not link to the second coil. So as a result, K is 0.2. It's very close to 0. So it is called loosely coupled. That is only 20% of the flux generated is linking the coil number 2 here, and here it is 90% or 100% of the flux generated in one coil is linking the other coil. So this is how you can distinguish the different types of coefficients. So, and the coils can be connected in series and coils can be connected in parallel. So the coils can be connected in order to aid the EMFs induced, or in order to oppose the EMFs induced. But for example, if you want to cancel out some EMF, so what is that you have to do? You just have to change the direction of the direction of the current in the coils, so that one EMF tends to cancel out the other. So for example, if you want to add the EMF, so you have to connect in series aiding position. Clear? So like that, you can either connect in aiding position or you can connect in opposing position. So the coils can be connected in series and coils can be connected in parallel. So what happens when coils are connected in series aiding and a series opposition? So what happens? All the EMFs induced will have the same sign, that is a plus, and the equivalent inductance will be L1 plus L2 plus 2 times into M. Why 2 times into M? Because there is an EMF induced from the flux which is in the coil 2 linking the coil 1, and there is an EMF induced in the coil number 2 because of the flux generated in the coil 1 linked in the coil number 2. So like that, you can have two mutual inductances. So therefore, the total inductance in series aiding will be L1 plus L2 plus 2M. Okay. So in series, actually E1 and E2 are the self-induced EMFs, and E21 and E12 are the mutual induced EMFs. So they are opposing the self-induced EMFs respectively. As a result, the total inductance is L1 plus L2 minus 2M. I guess you can easily make out what is E21 and what is E12. So E21 is the induced EMF in coil 1 due to the flux in the flux change in coil 2. Similarly, E12, it is EMF induced in coil 2 due to the flux changing in coil 1. So like that, you can distinguish the self-induced EMF and mutual induced EMF. Yeah? This is based on Faraday's laws of electromagnetic induction. So similarly, you can have connections like this parallel opposition, so in parallel aiding. So here you can say, so this is a coupled coils connected in parallel aiding. That means current flowing in the two circuits will definitely try to add the EMFs induced in them. Therefore, you will get the equation like this. And the total inductance here in a parallel circuit will be L1 L2 minus M square by L1 plus L2 minus 2M. So I have not gone through the derivation of this part because it is out of scope of this topic. That is why I have left the derivation for you. So just try to concentrate on the EMFs induced directions and mutually induced EMF directions and the final value of the inductance. That is L equivalent. Okay. So in the second case, what happens? The currents try to induce EMF in different directions such that the EMFs gets cancelled to a certain extent. Therefore, the total inductance also reduces L1 L2 minus M square divided by L1 plus L2 plus 2M. So this is how you can have a connection of coupled coils, whether in series or in parallel. Okay. So now we have also studied one concept called as a dot convention. So the dot convention, why it is used? It is used to find the polarities of the voltages. Polarities of the voltages due to mutual inductance with respect to the voltages of self-inductance in coupled coils. This is a new concept for you, which is very basically used to determine the polarities of voltages due to mutual inductances and with respect to the voltage of self-inductance in the coupled coils. So it depends on the marking. For example, if you want to know the transformer, if you have a transformer nameplate reading, you will have three phases marked with the dots. That is depending on the dot convention. That is based on the dot convention like this. And for example, in this case, what is happening? A current is entering the dots here. That is I1, and the current here, they also it is entering the dot here. So what does it understand? The EMFs induced and the mutual EMF generated are aiding each other. That means they are in the same direction of self-induced EMF. Okay, that is the mutual induced EMF and self-induced EMF are having the same directions or same polarities. For example, if I change like this, so what might happen here? So here also this is I1 and here also this is I2. So the dots, the currents is leaving the dots here, I1 and I2 the current, the I2 the current here, that is also leaving the dot here. As a result, again the mutual induction, the mutual inductance EMF, or mutually induced EMF will be in the same direction as of the self-induced EMF. This is the first case. So where exactly there are opposing EMFs altogether. Okay. So next is I'll take one more example so that you will understand it better here. So for example, here I'll take here, and this is I1 and this is I2. In this case, what is happening? I1 is leaving the dot in the first coil, and I2 is entering the dot in the second coil. So what happens here? The mutually induced EMF will oppose the self-induced EMF in this coil, the second coil. Okay, this is how you can understand the concepts here. Okay, so next, same similar example I can take here. So what happens here? So I1 here, and I will take this I2 here in this direction. So what you can say here? So I1 is entering the dot and I2 is entering the dot. So mutually induced EMF polarity is same as the self-induced EMF. You just have to check for the current leaving and entry into the dots here. Clear? So I guess it is clear for you. Let us solve some problems here and conclude this topic today. Okay, the problems will be based on simple KVL and application of loop analysis or mesh analysis. That's all. Okay. So the first problem I can take here. So it is find the voltage across 5 ohm resistance. 5 ohm resistance. Um, 5 ohm resistance. So if dot convention is given, you have to assume that it is a magnetically coupled circuit. If dot conventions are not given, that means it is not magnetically coupled. Okay, so if dots are present, if the dots are present, or if it is explicitly said, if it is explicitly said, how it is explicitly said? It is said in terms of the K values, it is said in terms of the mutual inductance values. If it is not given, you have just assumed that there is no mutual coupling between any of the elements present in the network. Okay, so this is J5 ohms and this is J10 ohms and this is 5 ohms here. And the dot conventions are given like this. This is dot here and this is dot here. Okay, and the current is flowing like this. I1 the first loop and I1, I2 in the second loop. So what is happening here? And one more parameter is given for you. That parameter is K. K is 0.8. Okay. So the J5 coil and J10 coil are mutually linked and having a coefficient coupling as 0.8. So the coefficient of coupling between J5 coil and J10 coil is 0.8. That means 80% of the flux is linking each other. 80% of the flux is linking each other. Okay, so you can calculate the mutual inductance like this, or you can calculate the reactance, mutual inductive reactance you can calculate. So M is equal to K times into square root of L1, L2. So obviously it is K times 0.8 into square root of it is 5 J5, that is inductive reactance is given. So what is that? This is nothing but what inductances, L1 and L2 are inductances. You have to calculate the inductive reactances. So it nothing but J omega L1 into J omega L2. Okay, so you can calculate like this, and it happens to be J omega M. So I write here it is nothing but J omega M. I write here in the next slide. So this is equal to J omega M is equal to what? 0.8 into J omega L1 into J omega L2. If you substitute it, so it is nothing but JXM is equal to J 5.66 ohms. Therefore, XM is equal to 5.66 ohms. Okay, so this is how you can calculate the X here. XM here, that is XM is nothing but mutual inductive reactance, mutual reactance, or you can call mutual inductive uh, reactance, you can call. So the currents are entering here in the first case. In the second case, current is leaving. So obviously, the mutually induced EMF between the coils will oppose the self-induced EMF here. Okay, so the self-induced EMF, how can you write the self-induced EMF in J phi coil? It is nothing but L into di by dt, L into di by dt, or you can write the drop. You can write as X into I1. Okay, so let me write that equation for you. So let us apply the KVL on the first loop here. Follow me here. So this is 50 angle 0. This is 50 angle 0 here. So it is 50 angle 0. Okay, the drop here you need to write the drop here. It is minus of J5 into I1. Okay, and minus of 3 minus J4 into I2. 3 minus J4 into I2. And this is with respect to what the currents flowing in the coils, J5 coil and this branch here, and drop in this branch. This is a drop in the J5 branch, and this is the drop in 3 minus J4 ohm branch. So I need to find the drop across the mutual inductance. How to find the drop across the mutual inductance, and what is the polarity of the mutual inductance? What is the polarity of the mutually induced EMF? So it should oppose. It should oppose the. It should oppose the self-induced EMF. The self-induced EMF is nothing but drop across the J phi. So it should be plus into J into 5.66, that is XM, multiplied by the current. How the EMF will be induced, that is due to the current flowing the second coil, that is I2, that is equal to what? 0. So this is how you can solve for the equation here. So now what happens here, if you just simplify it, you will get one equation. So this is equation number 1 here. So I repeat this equation here. So 50 angle 0 happens to be the voltage rise. That is why I have written like this. And the drop across this inductance, that is J5, that is minus J5 into I1. And here it is minus 3 minus J4 into I2. Again, it is I1 minus I2, sorry. It is I1 minus I2. So I just missed it. It is current 2. There are two currents here. So it is I1 minus I2. So, and here one more quantity, the new quantity here due to the mutual inductance. So J 5.66 into I2, that is equal to 0. So if you just simplify it, you will get one equation. That's all. And next, coming back to the next equation. So for the second case, for the second loop, you can apply KVL similarly, and then you can simplify it. Okay, so I will just apply the KVL on the second part here. It is minus of 3 minus J4 into I2 minus I1. This is the first drop in this branch, and next coming back to this one, it is self-induced EMF in the coil, so it is minus of J10 into I2, and here because it is opposing, so the polarity is minus here, obviously you get plus into J 5.66 into I1, and minus 5 into I2, that is equal to 0. So what is this term? This term happens to be the quantity related to the mutual inductance. In the previous case, this term relates to the quantity as mutual inductance. Okay. So this is a new term here for you. The rest of things are same here. So you can solve for here I1 and I2. You will get the current flowing through the 5 ohm resistance. Okay. So this is how you can solve it. Yeah. Yes. So next, one more problem we can solve here. Find the voltage across minus J10 ohms in the circuit. So find the voltage across. So here we were supposed to find the current here through 5 ohms. Now in this problem, we have to find the current here I, and in the next problem, so let me write the circuit first. So it is 10 angle 0, 10 J3, J8, 10, 10 angle 90, and minus J10. So you are supposed to find the voltage across minus J10. That means voltage across minus J10 you have to find out. Okay, and also it is given like this. So the dot conventions are given like this. Okay, so let the currents be here I1, and let the current be here I2. Okay, very simple. In that case, you can just apply the KVL here, the first loop. So it is 10 angle 0 minus of 10 plus J3 into I1 is a self-induced EMF, and here it is minus J10 into I1 minus I2. And there is one more quantity given to you, that is J3 ohm. J3 ohm it is given to you. So it is mutual inductive reactance. Mutual reactance or mutual inductive reactance J3 ohms. You can it is given to you. It is visible on the network. So here what is happening here? The current is entering the dot here. The current is leaving the dot here. So obviously the sign will be opposite. So plus into, so M is what J3, XM is what J3, that is into what I2, that is equal to what 0. Okay, so simplify for this one, you get equation number 1. Next, repeat the same. Repeat the same for the second loop. Repeat the same for the second loop. So it is minus J10 into I2 minus I1, and minus J8 into I2, and minus 10 into I2, and minus 10 angle 90, and plus mutual inductance is J3, and obviously into I1, that is equal to 0. This is equation number 2. You simplify for I1, I2.
Excuse me, sir.
Yeah.
Sir, that is minus J10 or plus J10, sir, in the center?
Minus J10. Correct? Hello?
Sir?
Yeah, okay. Any doubts?
Sir, that capacitance is there now, sir.
Yeah, minus J10.
Okay, sir.
Okay. Okay, that means
In the equation, it
yeah,
should be.
minus of minus, minus of
Yes.
minus. Correct, correct, correct. It is minus of minus. Perfect. Because it's a drop, no? So it is minus of minus. Clear? Is now it is clear?
Yes, sir.
Yeah. So you'll solve for I1 and I2. Then you can solve for the voltage across minus 18 ohms. So voltage across minus J10 ohms is equal to minus J10 into I1 minus I2. Okay, so this is how you can solve for it. Okay, yes. So now one more. These are the variants. These are the variants you can expect in this topic. Very simple topic. Okay. Next, one more problem. You can be asked to write the conductively coupled circuit. Obtain the conductively coupled circuit. Obtain the conductively coupled circuit for the network. Like that, it will be given for you. So you will have to write the conductively coupled circuit. That's all. Okay. So let us solve the problem in that case. So same circuit you can expect a two mesh circuit. So it is marked here and marked here. It is J10, J5, 5 minus J4, and mutual reactance is J5 ohms, and this 100 angle 30, and it is 10 volts. This is the resistance. This is the resistance. 10 ohms. So what is that you have to write here? You have to write the conductively coupled circuit or conductively coupled equivalent circuit. So you will have to write. That means you will have to write a circuit like this. So one impedance representing the self-inductance here, and other impedance referring the self-impedance in the second coil, and the mutual inductance between the two coils, and the voltage here, 100 angle 30. So your job is to find Z1, and your job is to find Z2, and your job is to find Zm. This is what the conductively coupled equivalent circuit. So how to obtain this one? You can either apply KCL for loop 1, or you can apply KCL to loop 2. You will get an equation. You get an equation. From that equation, you will have to identify the self impedance and mutual impedance. The mutual impedance is Zm, and Z1 and Z2 happens to be the self impedance. Okay, so Zm is what mutual impedance, and Z1 and Z2 are what self impedances. Okay, so what is that you can find out, just apply KVL in the circuit. Yes. Now you can write the KVL here, I1 and I2. So apply KVL here. So it is minus of voltage rise is plus here 100 angle 30 and minus J10 into I1 minus of y minus J4 into I1 minus I2, that is equal to 0. And one more point we left out, that is mutual inductance. So that is, and here the currents, one current is entering here, one current is leaving here. So obviously, the mutual induced EMF will oppose the self-induced EMF. So it is J5 plus J5 into I2, that is equal to what? 0. Let's simplify here. So it is 100 angle 30. Take common factor I1 minus J10 minus 5 plus J4 and take common factor I2. It is minus into minus plus 5 minus J4 plus J5, that is equal to 0. So let me carry forward this equation on to the next slide. So what happens here? This is equal to 0. Simplify. 100 angle 30 is equal to, or 130 plus I1 into 5. 5 minus J6 minus 5 minus J6 plus I2 into 5 plus J1, that is equal to 0. Okay, so this is how you can get the first part here. Okay, and you transfer this on to the right hand side. So it is 100 angle 30 is equal to 5 plus J6 into I1 and minus 5 plus J1 into I2. This is one equation. Okay. So now let me apply KCL or KVL to the second loop. Let me apply KVL for the second loop. So apply KVL to loop 2. So it is minus of 5 minus J4 into I2 minus I1 minus J5 into I2 minus 10 I2 and plus J5 into I1, that is equal to 0. This is the component due to the mutual inductive reactance. So let me simplify this one further. So let me simplify it. Take common factor I1 here. So minus and minus plus 5 plus J4. Okay. Plus J5. Minus into minus plus and 5 minus J4 here. Sorry. 5 minus J4 plus take common factor I2 minus J5 minus 5 plus J4 and minus 10, that is equal to 0. Okay, simplify I1 into 5 plus J1 plus I2 into this minus J5 minus J5 plus J4 minus J1 and minus 15, that is equal to 0. Okay, so this is another equations you got. So this is equation number 2 here. Just take this equation number 2 and equation number 1 here. Okay, so you have to take this equation, which is 1, okay, compare this equation 1 and equation 2. So what is common here? Common element you can check here. This is the factor which is common. I'm writing here 5 plus J1, it is common. So this happens to be the impedance. This happens to be the impedance. This happens to be the impedance, mutual impedance between the two coils. Because this coefficient is a very important thing when compared to the other coefficients, because it is common between the two coils. So as a result, you can denote Zm as 5 plus J1, Zm as 5 plus J1. Okay, and you can take Z1, you can further simplify and take Z1 and J5 and Z2 as 10 ohms. Okay, if you add it, you will get Z1 2 and Z2 1. So for example, if you take this one as Z11 and this is Z12, and this is Z21 and this is Z22. Okay, so obviously Z12 is equal to what? Z21. Z12 is equal to Z21. Though they are opposite in sign, we can just multiply this to the second equation by -1. You get the same thing. Okay, so what is that? You have to concentrate here. You have to find out Z11 and Z22, and from that you can make out Z1 and Z2. If you solve for Z1 and Z2, you will get J5 and 10 ohms respectively. This is how you can find out the conductively coupled circuit. Okay, so you can expect a 3-mesh network, or you can expect the same problem based on the network parameters. Very important because until now you have been solving the problems. Now you are making out the different elements, that is self inductance, mutual inductance, like that. Yeah. Yes. So if you got any doubts, you can ask me. These are the two variants in this concepts. Now let me solve one more problem here. Simple problem, which will make you to understand the concept of coupling circuits. This is 4 Henry, 5 Henry, 3 Henry. This is a point here, the point here, dot here, and this is the dot. Okay, and the mutual inductance between these two coils is 2 Henry, and mutual inductance between these two coils is 2.5 Henry. Okay, this is A, this is B, and plus and minus you can write down. Now apply KVL like this in this fashion. So the voltage across this inductance is L into di by dt. So let this be current be I. So minus 4 into di by dt. Okay. Now there is a mutual inductance. So the EMF induced will oppose the self-induced EMF in this coil. Therefore, you will get plus 2 times into di by dt. Why? Because the current is leaving this coil but entering this coil. Therefore, the mutual inductance will have an opposing character. Okay. Next, coming back to this coil, I'm in the coil 5 Henry. So it is minus 5 times into di by dt. And how do you write this and this? Again, it is plus 2 times into di by dt because of this mutual inductance. Next, coming back to this coil, just check out here, the current is entering here and the current is entering this coil. So obviously the induced EMF due to this 2.5 Henry has to be supportive for this one. So obviously minus 2.5 di by dt of same direction. Okay. Next, coming back to this coil, is minus 3 times into di by dt. Okay. And again, similarly, this one branch is minus 2.5 di by dt and plus v, that is equal to what? Z. Yeah. So this is how you can calculate the total EMF induced in this circuit, and ultimately you can calculate L effective. You add all the things, you get the equivalent inductance. Okay. Yes. Any doubts here?
Can you explain it once again, sir?
Yeah. So I will do it. Just follow me here. So minus 4 into di by dt is the self-induced EMF in coil of 4 Henry. And in this coil, the current is leaving the dot. In the second coil, the current is entering the dot. As a result, the mutually induced EMF will have to oppose the self-induced EMF in the first coil and also on the second coil. So what is the self-induced EMF in the first coil? It is minus 4 di by dt. So what is the mutually induced EMF between these two coils? It is 2 times in di by dt. So it has to oppose the self-induced EMF. So the self-induced EMF has a polarity negative. Obviously, mutually induced EMF has to be of positive. That's all. This is for the first coil. Coming back to the second coil, similar thing would happen. The self-induced EMF is minus 5 times into di by dt. So obviously, the current has to the current in this coil would produce the voltage in opposite to this self-induced EMF. Therefore, minus and plus here, similar to the first coil. Okay. Next, the coil 5 Henry is mutually linked to coil 3 Henry. So how it is mutually linked? Just check out. The current in the 5 Henry coil is entering. The current in the 3 Henry coil is also entering. As a result, the mutually induced EMF will be supporting the self-induced EMF in coil 5 Henry and coil 3 Henry. Okay. Therefore, minus is minus pi into di by dt, and will have the same direction, minus 2.5 di by dt. Okay. And coming back to the last coil, self-induced EMF, it is minus 3 di by dt, the self-induced EMF, and you will have some mutually induced EMF due to the mutual inductance, that is minus 2.5 di. So I guess okay. So in the next class, what we shall do, we shall take up the Laplace transforms. Laplace transforms, fundamental things. So I will leave it to you: initial value theorem, final value theorem, and Laplace of
Sir,
yeah.
sir, ಇನಿಷಿಯಲ್ ವ್ಯಾಲ್ಯೂ ಥಿಯರಮ್ ಮತ್ತೆ ಫೈನಲ್ ವ್ಯಾಲ್ಯೂ ಥಿಯರಮ್ ಆಗಿಲ್ಲ ಸರ್.
ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಅಲ್ಲಿ ಆಗಿಲ್ವಾ?
ಇಲ್ಲ ಸರ್.
ಮಾಡಿಲ್ವಾ?
ಇಲ್ಲ ಸರ್, ಅದು ಸಿಲೆಬಸ್ ಅಲ್ಲಿ ಇಲ್ಲ ಸರ್.
ಸಿಲೆಬಸ್ ಅಲ್ಲಿ ಇಲ್ವಾ? ಓಕೆ, ಐ ವಿಲ್ ಚೆಕ್ ಔಟ್ ಇಫ್ ಇಟ್ ಇಸ್ ಅಪ್ಲೈಡ್ ಟು ನೆಟ್ವರ್ಕ್ ಅನಾಲಿಸಿಸ್ ಅಂದ್ರೆ ಮಾಡೋಣ, ಸೊ ಇಲ್ಲ ಅಂದ್ರೆ ಬೇಡ. ಓಕೆ, ಸೊ ಅದ್ರ ಔಟ್ಪುಟ್ ತಗೋಣ ಅಷ್ಟೇ. ಥಿಯರಮ್ದು ಕಾನ್ಸೆಪ್ಟ್ಸ್ ತಗೊಂಡು ಇದು ಮಾಡೋಣ, ಡಿರೈವೇಷನ್ ಮಾಡೋದು ಬೇಡ. ಓಕೆ
ಓಕೆ ಸರ್.
So now Laplace transform I will start from the next class. Another 3 classes or 4 classes for Laplace transform, and another 4 classes for the Fourier transforms. Okay, 10 class, maximum of 10 class is required for me. So anyways, we'll have some time in the next week also, so we shall do it. Clear? If you have got any doubts, you can ask me, else you can exit for the next class.
Thank you, sir. Thank you, sir.
Yeah, I'm sharing the videos, lecture videos through a link to my Google Drive.